All right, I have another impact problem for us. So what we have here is a golf ball tester. It consists of a half-meter long rod, which has a 6 kilogram mass, and it is fired from the horizontal position. So it isn't just starting from rest and having gravity pick it up. We need a machine to fire this off at a given velocity. We're going to figure that out. And then, with the help of gravity, it continues to come down. And then, so here's state one, it's fired out of its position. State two is just before impact. And then state three would be post impact. Okay? So, I have those listed here. One, fire it. And that's writing. This is a former exam problem, so that's the wording we had before. 2, pre-impact, 3, post-impact. All right, so the golf ball, 0.05 kilograms. We have a coefficient of restitution here, so we've got some impact. We're going to be using momentum. And so the problem is A, find the speed to fire the rod where omega, just prior to impact, so this is omega at state 2, is 46.43. So omega down here, we're given. So we need to find what is V here to get the omega we want down there. All right? And then what is the golf ball velocity post-collision or post-impact? All right. So let me just straighten up my notes here. So the rod is rotating about O, so we're going to take our moment. We're going to get the mass moment of inertia at O, which will be 1/3 ml squared. So we have that here. All right. And we need to, here we have this rod, and it's got to drop through a distance to produce a given velocity here. So we have velocity, distance, this is energy to go there. And so that's what we have here. So we have 1/2 I omega squared, so that'll be the initial kinetic energy we require. We just computed I at O, the mass moment of inertia. So we want to figure out this omega. The potential energy here is the 6 kilograms times gravity times, this is 0.5 meters, so relative to the ball up, it's 0.5 meters up. So I'm taking ground to be my zero reference. All right. And then when it hits here, it's going to be 1/2, and here we had 0.5 for IO. And here's the omega we want just prior to impact. And then when this drops, the center of gravity will go from 0.5 meters up to 0.25 meters up. So here's the equation, one unknown. Solve for omega. It says we need to fire this thing out at 45.79 radians per second. Or the velocity right there is 22.89 meters per second. All right. So we've got part one, and then the next question is golf ball velocity post-collision. All right. So the velocity of the rod pre-impact. So at the base of the rod, we know omega times 0.5. So we have 23.215 meters per second coming into the ball. The ball prior to impact isn't moving, it's still. So when we go to use the coefficient of restitution, we have, I set it up with the ball post-impact minus rod post-impact down at the bottom. Then here we have rod prior to impact down at the bottom minus ball. So they're always in diagonals like that. Solving. We come up with 16.25 equals the ball post-impact minus the rod post-impact. All right? So what we typically do when we do these problems is we get one equation off of the coefficient of restitution. We get the second equation off of conservation of momentum. Because when these things impact, you have the angular momentum, the forces and moments are here such that there is no external moment. We're going to take angular momentum here at O, And there are no external forces that create a moment here. The forces are internal, they cancel, and any external moments are the time of the impact is so short that if you were to integrate it, you get a zero. So that's the normal assumption when you have impact. It's very fast, and so we say momentum is conserved. All right, now because this is rotating, we can't use, this is translating, but we have to use angular momentum because this one is in rotation. We cannot use this in any way with linear momentum. All right, so we're rotating about this point, so we'll go at O. That will give us 1/3. Well, we did that already, so we have IO. So the initial momentum, this is state 2 here, so this is pre-impact. So IO is 0.5, omega 2 was this given 46.43 radians per second. All right, what is the ball? Well, the ball's not moving. It would be, it has no omega, and it has no velocity at its center. That would be r cross mv. And here I note I have r, m, v, 0. Now v will be going over to the right, so r cross v will be a positive, which I reflected there. But at the moment, nothing's there. So then we go post-impact. All right? So then you'll have IO, which is 0.5, and then you'll have the velocity of the rod at the end divided by 0.5. Okay, I gotta have to have everything in terms of velocities, so rather than put omega in here, I just said what is the velocity at the end of the rod after the impact divided by the radius, and that gives me omega. And then by the same token, again, I have r cross mv, so we have r is 0.5, m is 0.05, velocity of the ball is to be determined. So there we go. So I get an equation here. I have an equation here. Solve. And we wind up with the ball post-impact, 38.5 meters per second. And we'll have another problem here in just a moment.